By now, we've become familiar with the concept that an object moving has energy because of its motion. We call that kinetic energy. So here's some mass m, and it's moving with speed v, and we know it's got some energy associated with that motion, kinetic energy, 1/2 mv squared. If we have some mass, maybe let's keep it really simple. Let's make it some mass on a massless rod, and it's rotating about its center point here. So that's the axis of rotation, and the rod is massless, and we just have these 2 point masses out at the end, and they're spinning around like on a baton, spinning around about its center point. It would make sense, even though they're not going anywhere, they're not translating, right? They're not moving in space, they're staying spinning around the same axis of rotation, they're staying in the same circular path all the time. They are moving, and we would expect them to have some rotational energy, some kinetic energy associated with this rotational motion. So let's view them, first of all, as 2 objects that are just moving in a straight line, because at any instant in time, that's what they're doing. So our rotational kinetic energy is just going to equal the kinetic energy of each of the items. 1 plus 2 plus ... if there were more. Right? This is going to be m1. This would be m2 maybe. So we would add up the instantaneous kinetic energies of each of the objects that make up our rotating system. So what is that? That's going to be 1/2 m1 times its velocity squared plus 1/2 m2 times its velocity squared. And if we had more masses, we would add them up. And what we want to do is get this, instead of in terms of their velocities, their instantaneous velocities, we want to get this in terms of its rotational speed, omega. When something is rotating, I'm going to have, let me just make the pivot point right here. There's my pivot point, my axis of rotation. And I'm going to carefully look at 2 points. I'm going to look at this point, this blue point, and this purple point out here. And as this thing rotates, as this bar rotates, at some later time, the blue spot has moved over and it's now here, and the purple spot has moved over and it's now there. The question is, which one is going faster? How do we describe speed for an object like this? And there are 2 answers, because there's 2 ways that we describe speed. The first response could be that both of these objects are completing the same angular motion in the same amount of time. In other words, both of these objects went through theta in the same amount of time. Or an easier way to think about it is, if I had waited until this object made a complete revolution, both of these points would have made a complete revolution in the same amount of time. So they're both moving at the same angular speed. And we use omega for that. Omega is the same for every point on a rigid object. If this rod is rigid and it's rotating, every point on that rod completes a revolution in the same amount of time. Omega is the same for every point on a rigid object. Now, another way of looking at it is that this purple line that I drew here is much longer than the blue line, and they both covered those distances in the same amount of time. So if we're thinking about distance over time, right, our translational velocity, distance over time, the purple spot covered a much larger distance in the same amount of time that the blue line covered. So the further out you are, the further you are away from the axis of rotation, the larger the distance you're going to cover in the same amount of time. So I'll call this R1 and this R2, the distance to that location. So the larger the distance from the axis of rotation, the faster the linear speed, because that point has to cover a larger distance in the same amount of time as a point closer to the axis of rotation. So we end up with a relationship that says our velocity, our linear speed, or some people say the tangential speed, is equal to r times omega. So omega is the same for every point on a rotating object, but the ones that are further away from the axis of rotation, r is the distance to the axis of rotation, and omega must be in radians per second. I told you with kinematics equations you could choose degrees, radians, revolutions, you could pick whatever made sense for the problem. But for this relationship, omega must be in radians per second. We also can relate our acceleration to our angular acceleration. We use a similar relationship, a is equal to r alpha, where alpha must be radians per second squared. And the reason for that is that we use, in deriving these relationships, we use this. So if this is an arc length, I'm trying to draw an arc length there, we'll call that s, and this is the distance, and that's theta. We know that arc length s is equal to r theta if theta is in radians. And we use that relationship in deriving these other two for velocity and acceleration. So that's why you have to be in radians for those two. If you are always in radians, if you just want to make that blanket conversion, everything in radians, you'll be safe for everything. But there are certain relationships where you have to be in radians, and others, like the kinematics equations, where you can pick whatever's convenient for you. Alright, so let's go back to our problem now. We want to get our kinetic energy in terms of this rotational quantity, this rotational speed omega. So let's do that. I'll come on down here, and what did I say? I said k rotational is k1 plus k2. Now I'm saying that this velocity is r omega. And omega is the same no matter where we are on our object that's rotating. So I'm not going to use subscripts. M1 might be a different distance to the axis of rotation than M2, so I'll use R1 and R2. Now I'm just going to rearrange this a little bit. I've got a 1/2 M1 R1 squared, omega squared, and I've got a 1/2 M2 R2 squared, omega squared. Now I'm going to add them all up. So I've got a 1/2, I've got a sum of all my masses. These are for point masses, because I said I could have more than 2. I could have 10. I could have 20. I add them all up. Each mass multiplied by its distance squared to the axis of rotation, and I add them all up. If this object is not made up of individual point masses, if it's a solid object like a rod or a ball or a disc, and it's rotating, then this summation turns into an integral, and you integrate over the rigid object. But I'm not going to do that right now. What I'm going to do is I'm going to say that this is very similar to our translational kinetic energy. This is our rotational kinetic energy. And we know our translational kinetic energy is 1/2 mv squared. V is our linear velocity. Omega is our rotational velocity. So we have a velocity squared term. We have the 1/2 out in front. And here we have our inertia. M is inertia. Right? That's how we measure inertia, mass. It's our quantitative measurement of inertia. Maybe this thing in parentheses is a rotational equivalent of inertia. We have now introduced a rotational inertia. So what does inertia do? It resists changes in motion. If something is at rest, it wants to stay at rest. It doesn't want to accelerate. It doesn't want to begin moving. And if something is not rotating, it does not want to start rotating, right? It has some rotational inertia. If something is moving in a straight line, it wants to continue to move in a straight line. That's inertia. We measure that with M. If something is spinning, maybe a bicycle wheel spinning about its axis, it wants to continue to spin. It has rotational inertia, unless some force acts on it and causes it to slow down or speed up. It wants to continue to spin at the same rate forever. That's rotational inertia. For point objects, rotational inertia is just mr squared. We typically use I, capital I, for rotational inertia. What do we have for our rotational kinetic energy? We usually write it this way. We replace our inertia m with the rotational inertia I. We replace our translational velocity v with a rotational velocity omega, 1/2 I omega squared, rotational kinetic energy. And there's one more thing we need to talk about before we can do some rotational energy problems, and that's rolling. Because oftentimes we use energy to solve a problem where we have a disk rolling down a hill, for example. And it's a fairly straightforward energy problem, but let me explain to you how we view rolling. It makes it a little simpler to do those problems. Rolling is fairly complicated motion. I'm just going to have an object rolling on a flat horizontal surface. And what's really happening at any instant in time is that there's rotation about an axis of rotation that's right there. This whole thing is rotating about an axis of rotation here. And that's fairly complicated to figure out. Coming up with the rotational inertia is not easy. It's not the end of the world, but it's not as easy as coming up with rotational inertia about its center point, for example. But the interesting thing is that when this object is rolling, when it's pivoting about the point that's in contact with the surface, that's equivalent to, that's identical to breaking this up and making two motions. One that's pure translation. So this is rolling, and this is pure translation, no rotation. Plus the object spinning about its center of mass. Pure rotation, no translation. Instead of viewing something as rolling, which is a little complicated, we can break it up and say it's the same as if the entire object was moving without rotating, plus the object rotating without moving. The kinetic energy of something that's rolling is equal to k translation plus k rotation, where the velocity of the center of mass is equal to r times omega. Let's, just for simplicity, make this object a hollow hoop, kind of like a bicycle wheel, where all the mass is in the rim and it's basically hollow, maybe a few very light spokes in there, but it's basically a hollow hoop. Then we get the kinetic energy due to rolling is going to be 1/2 its total mass times the velocity of the center of mass squared. The rotational inertia, we can look that up in our textbook. It's mr squared. And omega, I'm going to use this relationship right here. So we get twice the energy that if it was just moving. If it's moving and rotating, we end up, in this case, with twice as much energy. If I is different, we would end up with a different value here. This is because we had a fairly simple I of mr squared. This might seem a little weird right now, but as soon as we do some problems where we have objects rolling, and I show you how to account for the energy as two terms. When something is rolling down a hill or rolling on a flat surface, we add two terms to our energy equation, one for the translational motion and one for the rotational motion. We view them as being independent. And the fact that they are connected by this yellow box, V equals R omega, that makes it all work. And this only works when something is rolling without slipping. If it slips as it rolls, then this relationship in the yellow box is no longer valid, and the situation is much more complicated.